Welcome back, Pre-Calc. Hope you all are well. Our objective today is going to be to find geometric series. I've got the checklist on the screen. You know what to do from here. All right, I'm going to force another pause on the screen. Can you go ahead and write these three pieces that I am underlining? Go ahead and hit continue when you're ready. All right, so just like with arithmetic sequences, we'd like to find a formula for the sum of the first n terms. So a sub 1 plus a sub 2 plus a sub 3 all the way to a sub n. For arithmetic, remember we looked at little Gauss's way of comparing up sums that all have the same sum as the first and the last term. This one I don't have as cute of a story, but let's see if we can find a formula nonetheless. So if I want to find the sum of the first n terms, that's going to be the first term plus the second term, which remember is a sub 1 times r to the, just r to the 1 or just r, plus the third term, which is a sub 1, and then I need to multiply r twice, plus the fourth term, which is a sub 1 r cubed, and so on and so forth, until I get to the nth term, which is a sub 1 times r to the n minus 1. Remember that the second term you multiply by r once, the third term you multiply by r 2 times, the fourth term you multiply by r 3 times, and so the last term, the nth term, you would multiply by r n minus 1 times. Okay, now we're going to do something that's going to look a little bit weird at first, but I think you'll see why we're doing it in just a bit. So now what I want to do is take this S sub n row, so all these terms, and I want to distribute another r through that, okay? So if I take this first term times r, I'd have a sub 1 times r. If I take this term times r, I'd now have a sub 1 times r squared. This is going to be, if I multiply by r, a sub 1 times r cubed, and so on and so forth, right? A sub 1 times r to the fourth. And then my second to last term now would be a sub 1 times r to the n minus 1, and my last term would be this times r, which would now be a sub 1 times r to the n, right? Because this term times r, I'd now have r to the n. Okay, so now, why did she do that? Well, here's what I want to do now. I want to take this row minus this row, okay? S sub n minus S sub n times r. Okay, so what's going to happen? Well, we're going to get some nice cancellation. Okay, so I've got a sub 1 here, and nothing that is going to remain, right? But then look here, I've got a sub 1 times r in this row and in this row, and I'm subtracting the two rows, so those are going to cancel. Okay, and then continue looking here. I've got a sub 1 r squared in this row and in this row, and I'm subtracting the two. So those are going to go away, right? These are going to go away. And I'm just going to keep working my way in until the last term here cancels with the second to last term here, right? And so all that's left when I subtract is going to be my first term in the top row, which is a sub 1, and then all that's left in the bottom row is the last term, and remember I'm subtracting the two rows, okay? And I'm trying to get a formula for S sub n, so here's what we're going to do. Let's factor out S sub n here on the left side. That leaves me with 1 minus r on the right side. And then on the left side of the equation, let's factor out an a sub 1, so that leaves me with 1 minus r to the n. And we're almost there, so to get s sub n by itself, I want to divide both sides by this 1 minus r, so s sub n is a sub 1, the first term, times the quantity 1 minus r to the n, all over 1 minus r, and that is our formula. So I'm going to force a pause on the screen. Go ahead and copy what I have here. Hit continue when you've copied it. All right, let's try an example together. I'm force pause on the screen. Go ahead and copy this. Hit continue when you're ready to do it together. All right, so I've got our two formulas for sums on the screen. This, remember, is the sum of the first n terms for arithmetic, and this is the formula we just found for the sum of the first n terms for geometric. Some similarities, both of them ask you to, or require, I should say, the first term, right? But the similarities sort of stop there. I mean, you do need to know how many terms you're summing up. You do need to know n in both instances. However, look here, for arithmetic, I need to know my last term. I do not need to know that for geometric. What I do need to know is my common ratio, which I did not need to know my common difference for arithmetic sums. So the two formulas are really, they're really quite different in a lot of ways. So make sure we really kind of keep them straight. Again, for arithmetic, I really think, how many pairs do I have? And then I'm going to take the first term plus the last term, that 1 plus 100 like Gauss did, okay? However, this is not the formula we are using for this particular question, right? This particular question deals with geometric, okay? All right, so for geometric, I need to know a sub 1, which is my first term. So what is a sub 1? A sub 1 is 10. All right, I also need to know r. What is r in this case? R is 4. I'm multiplying by 4 each time. And what is n? N is 7, because I wanted to find the sum of the first 7 terms. So coming to our formula, I'm going to find s sub 7, which is going to be 10, times the quantity 1 minus, and here's where I want you to be careful. Please put parentheses around your r value, because if r is negative and you don't put parentheses, you can get into some trouble here, okay? And n is 7, so that's my numerator, all over 1 minus r. We can just plug this straight into the calculator. I'm getting 54,610. And really think about the reasonableness of your answer, right? Maybe this seems pretty large. However, remember that geometric sequences are related to what kind of function? They're related to exponential functions. So these grow very quickly if your base is greater than 1. And then not only is it growing fast, but I'm also adding up all those terms. So that's how I get to kind of this large 54,610. Okay, let's talk about how would I write this in sigma notation. Well, if we want to do sigma notation, there's a couple ways to do it. But let's first remember, how do we write a sub n? Well, we take our first term, times r to the n minus 1, right? So if I want to take a sum here, I can use this, okay, if I start at n equals, if I start at n equals 1, right? So if I start at n equals 1 and I want the first 7 terms, then where do I want to end? I want to end at 7, right? And then here would be my formula, 10 times 4 to the n minus 1. And you can test it. If I plug 1 in for n, I get 4 to the 0, which is 1, and 10 times 1 is 10. So my first term is indeed 10, which checks out here, right? Another way to write this, by the way, if you would like to start at n equals 0 and stop at 6, then you can go 10 times 4 to the n. Okay, it just really is really just a matter of preference, and make sure you know how to do both for MyMathLab. All right, I'm forced to pause on the screen. Go ahead and copy. Hit continue when you're ready to do this together. All right, so we've got a sigma notation here of a sum, and we really need to figure out, first of all, is this arithmetic or geometric? So I need to know which of our formulas to use. Now, if you replace this k with an x and look at just the expression here, is that an exponential function or is it a linear function? It's an exponential function, and so whatever is being raised to that power, your base, is your r, your common ratio. Now, why don't we go ahead, and there's not very many terms here, but let's go ahead and find the first couple terms. So if I plug in 1 for k, I would get 1. If I plug in 2 for k, I get 1/4, and if I plug in 3 for k, I get 1/8, right? So the first term is 1/2, and what is your common ratio? Also 1/2. All right, so my formula goes that the sum of the first n terms is equal to the first term times the quantity of 1 minus r to the n all over 1 minus r. And don't be fooled here that you have some cancellation here or something. These are not, they don't have a common factor, so no cancellation here. So plugging in here, what would n be? N is 3 because I want to find the sum of the first 3 terms. You said your first term is 1/2. You said that r is 1/2 as well. N again is 3 all over 1 minus half. All right, and let's go ahead and plug this in, and you will get 7/8 here. All right, so what's different about geometric as opposed to arithmetic is that you might have an infinite sum with geometric that actually has a limit. So the infinite sum does actually converge. All right, so let's take that sum that we were just looking at, 1/2 plus 1/4 plus 1/8, and let's keep going. Let's keep going forever, okay? Let's take a look at what happens geometrically. All right, so here I have a square with area 1, and if I take, half of that, I now have that shaded in, and then I'm going to take half of that, which will be 1/4, right? Let me shade that in. Take half of 1/4, so shade that, this kind of empty piece, half of that, that's going to be 1/8. Shade half of the remaining will be 1/16. And keep going, and you can see that we get closer and closer and closer and closer and closer and closer to filling it in, but we never quite get there, okay? There will always be half of the empty space left. So what we say is that the sum converges to 1, which would be the area of that square there. So we do have infinite geometric series that converge, so they have a limit. Now, do you think that all infinite geometric sequences have a sum? And if so, why? If not, can you give a counterexample? So what do you think? Do they all have a sum? They don't, right? Like let's take, instead of multiplying by 1/2, what if we double? So 1, 2, 4, 8. If I take the sum of this sequence, this is going to diverge, right? It's not going to hit a certain limit. So with that in mind, what do you think has to be true about the common ratio r for the sum of an infinite geometric sequence to exist? Well, r needs to be smaller than 1, but it can also be negative. So here's what we say. We say that the absolute value of r needs to be less than 1. In other words, my common ratio needs to be between -1 and 1. And if that's true, then my infinite geometric series does converge. All right, so let's see if we can't figure out a formula for an infinite sum for a geometric series if r is between -1 and 1. Well, here's what I want you to do. There's only one place that n pops up in our formula for our finite sum, and that is in this term here, right? So if r is between -1 and 1, like let's take 1/2, like that previous example. If I take 1/2, let r be 1/2, and I raise it to the n, and n, my number of terms is going to go to infinity. Well, if I have like 1/2 to the n, this is the same as 1 to the n, which is 1, over 2 to the n. So bigger on top, bottom, or same? Bigger on bottom, right? And so this whole term is going to go to 0. So this piece here, when r is between -1 and 1, and n is going to infinity, this whole term goes to 0. And so the stuff in parentheses is 1 minus 0, which is 1. And so the numerator is just going to be a sub 1. So my infinite sum, if r is between -1 and 1, is just my first term all over 1 minus my common ratio, because the stuff in parentheses is all just going to simplify to 1. So I'm going to force a pause on the screen. Go ahead and copy what I have. Hit continue when you're ready to do an example. All right, so let's try that one that we were just doing with filling up the square. So we started with half the square, and then we added 1/4 of the square, and then we added 1/8 of the square, and we went on forever, right? So using my formula here, and we said that the limit should be what, by the way? Should be 1, because eventually it got closer and closer to filling up the entire square. So my infinite sum will be the first term, which is 1/2, all over 1 minus the common ratio, which is what? Also 1/2. So I have 1/2 over 1/2, which is 1, which is exactly what you predicted. Force pause on the screen, go ahead and copy example 3. Hit continue when you're ready to do this together. All right, so there are 2 conditions for these series to converge, to have a limit. 1, it needs to be geometric. 2, r needs to be what? It needs to be between -1 and 1. So let's take a look at A. Is this geometric? It is. What is r? R is 1/3. So does it fit? Is it going to have a infinite sum? Is the infinite sum going to exist? It sure is, because 1/3 is between -1 and 1. So my infinite sum is the first term all over 1 minus r. My first term is 45, and then 1 minus 1/3. I think these are faster just to do by hand. 1 minus 1/3 is 2/3. So dividing by 2/3 is the same as multiplying by 3/2. So my final answer is 135 over 2. All right, how about B? Is it geometric? It is, because this part here is akin to an exponential function, right? Okay, what is r? R is 0.4, so is the infinite sum going to exist? Sure is, because 0.4 is between -1 and 1. Okay, so my infinite sum is the and by the way, you can't type this into like an 84, is the first term. Well, let's find the first term by plugging in 1 for k. 1 minus 1 is 0. Anything to the 0 is 1, and 5 times 1 is 5, okay? And then on the bottom, I have 1 minus 0.4. So simplifying that out, we should get 25 over 3. All right, part C. Is it geometric? It is, right? Because the inside is exponential. Pi is your base, and you see your n is in your exponent. Now, what is r? R is pi. So will the infinite sum exist? It will not. So I'm going to put D and E does not exist, since pi is greater than 1, right? Pi is not between -1 and +1. All right, you all, that is all I have for today. I will see you next time.